All right, so this is Forestry 420 Park and Wildland Management. It's a beautiful September 13th, Monday. We're gonna do some map and compass orienteering and then talk about wildlife management relative to parks. So come on around the lake. All right. Let's let folks kind of bunch up here and we'll do the chalk talk as we walk. All right, so the basic idea here is this is an exercise in so-called spatial reasoning. There are lots of ways in which your brain works, and some folks are pretty good at reading, some are pretty good at writing, some are pretty good at arithmetic. Spatial reasoning is another type of cognition. So this is a way for you to use some basic analog or digital tools to figure out where you are on a map. And today's exercise is, as they say in Letterkenny, Ontario, super soft. We are pretty familiar with the landscape that the map is depicting today, and we should be able to intuit where we are on this map with a minute or less of just sort of looking at the map and looking around. But the skill set is building off of that intuition to learn the tools to do it not on autopilot, to make it an explicit skill-based process using your map, topo map specifically, and your compass. All right? So the first step is to, when you're using this in a professional context, stop moving and check around for any kind of hazards. So for example, if you're going to be working in a particular area and you need to verify that you're in the right place on the map, first thing you want to do is make sure that you're not standing by a ground hornet nest or right at the edge of a cliff, so as you look around you don't accidentally step off the quick way down, and so on and so forth. All right, so step one, as obvious as it is, look around. Are there any dead branches above you? And you should not be right there, and so on and so forth. Do you see any grizzly bear scratches on tree trunks or tufts of fur on the tree trunks nearby if you're working in bear country? Bears love to rub and scrape and scratch on trees to mark territory and just get comfortable as well. So come on around the lake here and we'll talk about steps 2 through 6. So on subsequent pages of your packet there, we've got a couple of things. One page is basically a zoomed in section of the 2021 Carbondale USGS Topo Quad. This is a particular kind of map that has lots of topo lines on it so that you can have a sense of the 3D shape of the land on a 2D planimetric, top-down, perfectly straight up and down view of that landscape. The topo lines are very faint gray on this printout of the topo map, and they are 10-foot interval contours. So where you see a circle or a oblate sphere or oblate egg type shape on the map and then another one wrapped around it, there's a 10-foot elevation difference between the points on those two lines. So you should be able to see some of the high country around the lake as you look at the map. All topo maps have 2 north arrows. One is a magnetic north, which is what your compass is going to tell you. The other is the geographic north, what the old school north arrow pointed to before we started correcting for things like magnetic drift. The semi-liquid nickel core of the planet is slowly rotating and moving, and it is a natural process that has happened many, many times for the magnetic envelope for the planet to flip its poles. It's drifting all the time. And so when you are out in the field doing forestry and you are using analog mapping tools to collect stuff because you're way off in the backcountry and batteries are heavy, or your cell phone got waterlogged and you got to go to your map backup or what have you, you want to make sure that the date on that map is relatively recent. Here in the Midwest, the difference between magnetic north and geographic north is just over 2 degrees. So you'll see a pair of north arrows forming a very acute or tight V shape on your map. And magnetic north on a topo map is straight up. The geographic north, which is sort of an artifact of how we make maps and not really reflected in reality, is the one that's off to the side. In this case, in our position on the planet's surface, it's off to the left or slightly west of north by just over 2 degrees. Okay? In other places, that difference is quite a bit bigger. As you get high in latitude, for example, that adjustment or declination can be pretty stiff, meaning your map, if it's not a topo map with magnetic north as up, you can tilt it 15, 20, 25 degrees and your measurements can be way off if you're not making that correction. For us today, we're doing fairly quick and dirty stuff just to kind of figure out where we are on the map with some degree of accuracy. So a 2 degree adjustment between geographic and magnetic north, not a big deal, but it is important to pay attention to that. Okay, so if you end up doing a summer job out in Alaska with the Forest Service, doing wildland fire prep work over the summer, keep that in mind for your maps. Magnetic is not the same thing as up on a non-topo map. Cool. One of the other pages is a scale bar, and I put it on a separate page so that you can rip that one out and literally use it like a ruler. We're gonna, at the end of this thing, get a sense of what's our accuracy, how close is our position estimate to our actual position in real space, and our precision. How well did our different measurements agree with each other? For those of you with the SIU Shooting Sports Club out at the pistol range, this is the tightness of the grouping. So you can have high accuracy and low precision and vice versa. They can both be low, they can both be high. Obviously we want high accuracy to know where you are truly on the map, and high precision, all the different measurements that you're going to take to get there. Each one is quick and easy, but they need to agree with each other. Otherwise, you don't know how trustworthy that position is. Okay? So, we're going to do a process of triangulation. We're going to take map directions to landmark points that are on the map and that you can see. We're going to need, at a minimum, 2 of those to get any kind of a position off the map. We're going to need at least 3 to have any sense of precision or how well your measurements worked. So we're going to find a couple 3 landmarks around, big things that are not moving, that also show up on the map, like points, ends of little peninsulae on our water body here, power line rights of way. Cemeteries are often marked on topo maps. Large buildings are often marked on topo maps. Big and small roads. When you use a road as a landmark, look for an intersection. It's hard to sometimes, if you're not real sure where you are on the map, pick the correct spot on the road. So look for characteristic sharp bends in the road where there's only one such bend on a particular road in the map, and you think you kind of see it over there, kind of thing. We would use that specific spot as the landmark, not the entire stretch of road. In the same way, we're not going to use the entire lake, because you could take an infinite number of compass directions to different spots on the lake. So we're going to pick one or a couple of those specific spots. So there's a small table in your packet where you can record each of these landmarks that you want to use, and everybody's welcome to pick their own. This is going to be a solo exercise today, not a team-based one. We'll fold back into our teams for talking about wildlife in a bit. So once you pick your landmarks, we're going to measure the compass direction to each of those. That's called an azimuth, or bearing, or facing. All different terms for the same idea. What direction, what number on the face of the compass represents the direction between you or from you to that thing. And then from there you record that number, whatever it is. And then you add 180 if it's less than 180, or you subtract 180 from it if it's greater than 180, so that you get the opposite direction that you're looking to the landmark. This would be the same thing as you standing at the landmark and getting the compass direction to where you are currently. But we can't do that. We are looking off to the landmarks and then getting what's called the back azimuth off of those, 180 degrees off of the direction from you to the landmark. And then on your map, use a pencil or a pen, and you can use the scale ruler or just a folded over section of your paper to make it a little bit thicker. Use it as a straight edge. You draw from the landmark along the direction of the back azimuth, the number that you calculate, not the one that you record from the compass. And you do that a couple of times. And those lines should, in theory, intersect. And you are where those intersect. So this is a bunch of like math and trigonometry. Yikes. But I promise the only real math that you got to do is adding or subtracting 180 from numbers. I believe in you. Okay? So we'll do at least 2 of those to find your position on the map. Make sure that spot that the map is telling you you're at agrees with your intuition of where you're at, based on having been around lovely Campus Lake in the past and knowing generally where you are on the map. And then repeat with landmarks 3 and 4. It is easier to get a more precise and more accurate set of plots or lines on your map all crossing where you are standing if you choose landmarks that are well separated from each other around the compass. So for example, if my first landmark is at 45 degrees due northeast from me, and my second landmark is at 47 degrees, and my third landmark is at 41 degrees, well then, I have to be extremely, extremely precise in drawing those bearings of those back azimuths to cross onto me. If there's even a little bit of slop on that, I'm going to be way off. Surveyors and foresters call that a collinearity problem. If all of your landmarks are collinear and approximately a straight line or a very narrow cone to each other, you're going to have a hard time getting an accurate position fix on your TopoMap sketch. The same thing is true with GPSs. When the satellites are in a straight line above you, your GPS doesn't know whether it's coming or going, because nanosecond level errors in figuring out the distance to each of those things, in basically the same process that we're doing now on a flat map with compass readings, that can put you thousands of miles in the wrong direction, because light travels at 186,000 miles per second in a vacuum. So small error translates to big error on the map when your landmarks are collinear or in a straight-ish line with each other, or in a narrow cone from you on the map. Make sense so far? All right, any questions so far? Cool. So, if you have a compass app on your phone, most of us do, you're welcome to use that. You can use the survey grade, so very accurate compasses in the class here, those yellow ones with the Clinos in them as well. And the digital compass in the hypsometer, the laser rangefinder, is highly accurate as well. We'll get that set up for you, and it's real quick, okay? So that everybody has a chance to use the compasses, once you've got your 3, 4, 5, whatever you want to do, landmarks measured out with the compass and what direction they are from you, pass it to the next person who's using their smartphone or just waiting for one of the tools, so we can all kind of try the different methods of this. They should all be equivalent, but you never quite know until you try it, okay? So let's head over here, and we'll head kind of to the water's edge so that we can see some landmarks in this entire direction over this way. Hopefully we'll find a spot with at least 180 degree view. All right. Here's our base of operations, this picnic table. We're going to plot exactly, individually, where this picnic table is on our topo map. So again, this is kind of easy mode, right? So we're in a familiar environment. We've got some really pretty clear landmarks. When you're out in the backcountry, your landmarks are more likely to be things like peaks or characteristic bumps along ridge lines. So it pays to have a good, recent, and zoomed way in topo map with tight contour intervals, lots of lines of information in there about elevation in different locations. So you can see the shape of the landscape on your map and then pick out along a ridgeline. Okay, so that's the third bump in a row. That's the one I'm gonna pick for my landmark, because we can't use an area to get a single bearing out of. We want smaller, highly visible features for that. Okay, cool. So everybody's gonna need to kind of rotate where you can see anything kind of in this entire swath. We can see back over here where we came from. We can see across Campus Lake to this side. We can see across Campus Lake towards Thompson Point, etc., etc. Okay, cool. Let's try this out. Pull up that Compass app on your phone. If you have one of the Compass Clinos, hold it flat in your palm and use one eye looking on the dial, one eye looking out. The larger of the two numbers that you see is the azimuth, or the direction that the compass is pointing in. The smaller of those two numbers on the compass is typically the back azimuth. Your azimuth plus or minus 180, so that number falls between 0 and 360. Okay? And feel free to, you can lay your paper down on the table here and make your records on there if you would like to.
So it doesn't matter what landmarks we use?
It does not matter what landmarks you use, as long as you pick some good ones that aren't right next to each other. And I expect we'll have some overlap with everybody, and folks are very free to pick things that don't necessarily map onto anybody else's. So again, if you're holding one of the yellow Compass Clinos, hold it flat in your palm, not vertically, so you don't want it to make a vertical capital P shape. You want to hold it flat so the compass dial lies flat with the window up. So it's lit by the sun.
So what is the top number, the azimuth?
The larger of the two, yeah, the top one.